All right. So what we're doing here is we're going to be deriving some equations for the bubble point and dew point using Raoult's law for an ideal composition, namely a liquid or vapor composition, whichever one we choose for the corresponding bubble or dew points. And then we're going to be modeling those equations in Python. Uh, yeah, let's just jump right into the derivations, I guess. So I guess it'll help to start with what is bubble point and dew point. So writing it out here, bubble point, we can have either a constant temperature or constant pressure. If we start with constant temperature, we'll have a bubble pressure, and that is happening as we are decreasing the pressure from a given liquid composition. We'll reach a certain point where uh, the liquid mole fractions, or I'm sorry, the vapor mole fractions sum up to 1, and as we decrease that pressure, the first bubble will appear. So that will be our bubble pressure. And then similarly, but inversely, we have at a constant pressure. This time we're modifying the temperature, so we will have a bubble temperature. And that happens as we are increasing the temperature, again, from a known liquid composition we're moving from the liquid phase to the vapor phase, so it makes sense that we have to increase the temperature to see, to see the first bubble, since you're going from a more dense phase to a less dense phase. And then we can also talk about the dew point. So now we're going to have a known vapor composition. So Yi known vapor composition. And again, similarly, we'll have a constant, we do constant temperature first again. That will be the dew pressure, since we are, again, modifying the pressure. Uh, I'm sorry, that's inverse. Since we are at a vapor already, we have to increase the pressure to go from a vapor phase to a liquid phase. And then inversely once more, if we're at a constant pressure, we will have a dew temperature as we modify our temperature, decreasing that temperature so that the molecules are less excited and they will come down from the vapor phase to a liquid phase. Check it. We're still recording. Okay. So yeah, let's go ahead, derive this, derive what we can at least with Raoult's law. So Raoult's law, what is Raoult's law? For an ideal mixture, we have the liquid mole fraction Xi times the saturation vapor pressure is equal to the vapor mole fraction times the total pressure, and as we know, that is partial pressure. So specifically starting with the bubble pressure, we have a known liquid composition that is our Xi here. And what we don't know is our liquid composition, but a way we can kind of get rid of that unknown is to say that at the bubble pressure, the sum of the vapor compositions must equal 1. So that's just kind of an algebraic substitution we can do. Kind of rewriting this in terms of summations, we have the summation of the liquid mole fraction times the saturation vapor pressure is now equal to just the pressure. And that's our dew pressure. That's our dew pressure that we're going to be solving for. All right. I guess while we're here, might as well do I'm sorry, I wrote dew pressure. That's bubble pressure since misspeaking, as you can see from the bubble point, we have a known liquid composition. So we have the Xi. So obviously that's going to be bubble pressure. I don't know if I want to derive both just here. Yeah, let's go ahead and just derive both. I'm kind of talking ahead of myself here, but to get the bubble temperature, we actually won't be able to use Raoult's law, but we will be doing a sort of iterating algorithm. We'll create a function for our bubble pressure, and then within that function, or using that function for the uh, the bubble temperature, we'll be making a guess to what we want our pressure to be, the pressure we input into that function, and then using SciPy, I believe it is the root solver, we're going to zero out that subtraction until we actually find the pressure, and that's how we'll get uh, the temperature, since it'll be the temperature at which the bubble pressure matches our pressure that we give the bubble temperature algorithm. It'll probably make more sense once I go type it on the code. But while we're here, might as well do kind of the inverse for the dew pressure. So with dew points, we know that we have a known vapor composition. That's yi here. So instead of solving for xi, our liquid mole fraction, we're going to be trying to get rid of that. And the same way that we said that the sum of the mole fractions in the vapor phase were equal to 1 at the bubble point, bubble pressure, we can thus say that the sum of the liquid mole fractions is equal to 1 at the dew pressure or dew point where the appearance of that first, I guess, vapor appears. So doing a kind of similar substitution, we'll have the sum of, well, I guess, start from the beginning. So liquid mole fraction is now equal to 1. So we'll have a 1 there times the summation of the saturation vapor pressures is equal to the summation of our liquid mole fraction times our total pressure. And again, for dew pressure, we want to solve for this P pressure. So to isolate that, we will be doing a sort of, I mean, it's just kind of a division pretty much. So we'll have pressure saturation, summation of that divided by the summation of our liquid mole fraction is equal to our pressure. Let me make sure I'm not getting anything too confused here. That's 1. Yeah. And this should hopefully be the same thing as doing if you wanted to write it a different way. Yeah, because we'll divide by the reciprocal or multiply by the reciprocal. Yeah, dividing by a fraction, dividing by the denominator, and multiplying by the reciprocal, same thing. So yeah, just checking if we got any mistakes here. Oh, you can't see that. It's not too important, but I just rewrote it in case. All right, so I guess we could just jump right in to the coding. Yep, we're still recording. Okay. The best way I want to do this. We could do, you could see everything now. Let's just switch from this here. Nope, not that one. All right. A lot of tabs open here. And that's my practice run. So, I mean, let's just start a new notebook. New notebook. And then this will be our, yep, all right, recording, all right. So let's just call this bubble and do calculation. Make sure you can see everything here. Yes, okay. Let's get rid of this picture. What's the best way I want to do this? Find the technical difficulties. Okay, it's actually better, I guess. Okay. What I'm gonna do here is we have some pre-written code that we'll be copying over. This is mainly just for uh, basically we're retrieving properties from a GitHub repository, and uh, that will allow us to pretty much retrieve those properties for those compounds that we want from our question, and in doing so, we'll be able to kind of do these calculations relatively faster than we would without them, and especially for the saturation vapor pressure specifically. So that's that. Imported some libraries, NumPy, most commonly used one, and then Jax is this whole thing, simplifying it to the most basic understanding that I can say is we're turning these into 64-bit integers. All right, so now that we got those imported, let's go ahead and read the question once more. So we have a liquid composition of a 37 molar ratio of benzene toluene. Let's go ahead and make our array first. So we want to define I guess the best way to say this. I guess it's technically a list or, oh no, it is an array. That's my fault. Uh, but yes, it will be our xi liquid mole fraction is equal to our array of, I think we said 0.3 and 0.7. Is it benzene toluene? In that order? Yes, benzene toluene. So the reason I'm putting that 0.3 first, we do benzene toluene in the order of the most volatile component. So in the same fashion as we retrieve our properties, I'm going to define a variable called P, and that's going into our P equals props for properties, and it comes from right here. We're importing it from CHE5. Again, that's some pre-written code that has all those properties, and I can simply type in what I want to retrieve. I think I keep on forgetting benzene, the first one that we want to get, and toluene is the second one. Make sure these are brackets. Go. If enter. Oh, and by the way, if you don't know, we are in Google Collaboratory. It's kind of a open, I guess, in-browser coding you can do with Python. And as long as you have a Google account, you could just open up a browser, open up a tab, and start coding. It's pretty cool for that. So yeah, now that we have defined our properties, a cool thing we can do now is there's, I guess, a function that we can evaluate called p.pvap, standing for pressure or vapor, saturation vapor pressure. So p.pvap is evaluating both of these values in this list I created, and we can evaluate them. It takes in any temperature in Kelvin, so we can do 373.15. Hit Shift Enter, and we should get two values. So those are the pressures in pascals for benzene and toluene, the first and second correspondingly, at a temperature of 373.15. So in terms of what we actually want to do, we're going to, like I mentioned before, we're going to be creating a function for our bubble pressure. And I mean, let's just go ahead and do that. So define our function. So we'll call it, I guess, bubble P for bubble pressure. And then let's make sure we say this is ideal since we are using Raoult's law. And after we create that function, we need to define certain parameters. Technically, we can define as many as we want, but for the calculations we did previously, it was, let me change this so that, I wonder if I'm doing this correctly. That better? Yeah, so you can see what I'm looking at. Okay. So going back to our derivations that we did pretty much. So the bubble pressure was equal to the summation of the liquid mole fraction times our saturation vapor pressure. Well, what we just coded, or I guess what we could do so far with our code is get the saturation vapor pressures given a certain temperature. So like for pressure, we'll definitely want the temperature for the bubble pressure. The temperature is definitely one input we want, but another input that we want as well is that first element, the liquid mole fraction summation of that. So I'm going to be putting xi from the array we mentioned before, and then that will be those two parameters that we need for our function. So we're going to want to go ahead and return that function, or we want it to return a value from our function. So let's write our equation that we derived. So that is the summation of our um, liquid mole fraction times the uh, saturation vapor pressure. And that will be at a given T temperature. So hopefully this looks right. Yes, no errors yet. Awesome. So what we're doing, again, summation of our liquid mole fraction, xi, times the saturation vapor pressure given the T. And remember that those two are parameters in our function that we are also returning in the equation we use in our function. So if I go ahead and try to evaluate our function, give it the same uh, liquid mole fraction in the array we typed before, and give it a temperature similar to how I evaluate the P.P vap, we should be able to get the same thing, hopefully. Or no, I'm sorry, this is summing it up now. So this should be the 105,789 pascals should be equal to the sum of the two values in the array that where I evaluated them separately. But since this is a function and then I added a summation as well as a multiplication of the liquid mole fraction, this final value of 105,789 pascals is actually our bubble pressure. Awesome. So I think that gets the first question out of the way. So now for a liquid composition, we're doing the second part. We're going to be doing the bubble temperature. Um, so as I mentioned before, uh, we have kind of one equation, one unknown, and we kind of need to use a iterating algorithm known as Raoult from uh, SciPy, Science Python, another library like NumPy, in which it has multiple functions, but we're going to be focusing on the Raoult function to help us basically get that temperature that we want. So I don't know how we want to. I mean, let's just define our bubble temperature. So again, bubble temperature ideal, since we are using Raoult's law. Similar thing of using the liquid mole fraction, since we are still talking about bubble points, specifically here, the bubble temperature this time. And then since we are talking about the temperature, we will want to put in a pressure, again, constant pressure. And then the bubble temperature is that, as you remember, the bubble temperature is that temperature in which we increase our temperature all the way. I don't know why I did that. Increase our temperature to a certain point at a constant pressure, the first bubble will appear from a known liquid mole fraction composition. All right, so here we're actually, after we define our two parameters, we're going to define another function. And this is the iterating function I was talking about. We can call it, let's call it guess, I guess, since we are doing a sort of guess and check, kind of makes more sense uh, as I type it out, maybe. So we're going to be guessing a pressure given a temperature that we have. Make sure I'm not missing anything there. And then we're going to want to, again, return a value. We'll be using our bubble pressure function that we got. And remember that function takes two parameters, our liquid mole fraction and our temperature, and subtract this from a pressure that we are supplying for the temperature, the bubble temperature ideal. So go ahead and fix that. Make sure I'm still recording. Okay. All right, what's next? So now that we have our p guess, we'll need to do the Raoult algorithm I mentioned before. I think I might have actually have it pulled up here already, possibly. Yep, awesome. So it is scipy.optimize. What is it? You can pretty much just look up scipy.optimize.root on Google, and I'm pretty sure this is the first thing you'll find. But yeah, this is kind of the documentation. And what this does, it'll find when you take a root of something, you're basically finding the zeros of that function. So we're finding the zero of this equation and finding that temperature at which that satisfies zero for this calculation. So with the root function, we have some arguments or parameters we need to provide. So we have the function, the vector that we're going to be calling, and an initial guess here. And all of these other ones should be optional, yes. So we don't have to worry about those. So we're just focusing on the first two parameters, function and initial guess, x initial. So we could start with something like the root, or actually, I don't think I imported it, yes. So yes, when you use functions that are not inherently within Python, you will need to import them. Similar to all these import stuff I mentioned before, you will need to do this I guess in the beginning before you can use these other functions I'm using, like a NP array. So let's import that. So we're going to import from scipy.optimize, I believe is it as root, or I'm sorry, from scipy.optimize import root. I believe that is the syntax. I could be wrong. Let's just check it. Okay, it didn't yell at me, so hopefully that's right. uh, Bear with me here as I'm also kind of learning the coding syntax, but as we use the root function, okay, that works. We're going to be calling our pguess function. So like I mentioned before, we had two parameters. The function that we need to call, that is going to be finding the root of, and then the initial guess. So the first thing is our function, pguess, then our initial guess, x initial. It's going to be a temperature that we're guessing here. I could give it the answer I want, but let's just do 300 Kelvin, just so we make sure our code is not written in the way that it will only give us 373, since that was a problem I had earlier. So yes, so this line of code is taking the root function, or I'm sorry, taking the root of this function, supplying with the help of a initial guess. So if I shift evaluate this, it shouldn't do anything. Oh no, it's expecting. Oh no, that is correct. Okay, I forgot a semicolon there. But if I shift enter, it shouldn't do anything since we're actually not printing anything. But what I can do is let's just store this result as a result variable. So res, and maybe actually I can just return this, I'm pretty sure. So let's just return that. And it should, when we plug in our parameters for this bubble T ideal function, so I plug in our array from before and a pressure that we supply. So if we supply our pressure that we got, our bubble pressure that we got from our bubble pressure function at a constant temperature of 373.15 Kelvin, we should get that same 373.15, hopefully, yes. So we have some extra attributes here, but we're interested in this X attribute, the result. So actually what I'm going to do here is return only the .x attribute. And if I shift enter on both, it should only give me, awesome, you should only give me that temperature of 373.15 Kelvin. So that is pretty cool. That's the wrong tab. What else have we got here? So we saw for the 37 molar ratio and found the bubble pressure at 373.15 Kelvin. And we also obtained the bubble temperature. I'm sorry, one more time. So for a liquid composition of 37 molar ratio of benzene toluene at the pressure obtained. So we use the same pressure. Okay, so we were just iterating pretty much what we got in the previous function. So basically, once we supplied our 373.15 Kelvin into our bubble pressure ideal function, we received a pressure of about 105,000 pascals. And then in plugging in our 105,000 pascals into our bubble temperature function, we found going backwards pretty much say 373.15 Kelvin. So it's pretty much the inverse of each other if you kind of think about if we put in the same pressure that we receive at the bubble pressure, we should get the temperature that we get in the bubble temperature. All right. I guess next is pretty much the same thing, but with the dew pressure. So very, very similar in terms of what we're going to do. And we already derived it. So it's kind of just a plug and chug from here, since everything is working. So remember that for our dew point, we're starting with a vapor composition. So Yi this time is what we're going to supply into our functions, and then it's kind of pretty similar to there. And the only difference really is the calculation in the function itself. So let's go ahead and see, how am I doing on time here? Okay, 20 minutes, not bad. Okay. Where do we want to start? Actually, since we are doing also a liquid molar fraction and a vapor molar fraction, we can kind of just say change our array here to a z. And with chemical engineering, there's sort of a standard with how we name certain things. And Z represents typically a feed composition, and that could be either liquid mole fraction, purely liquid mole fraction that we used before for our bubble points, bubble pressure, bubble temperature. It could be a vapor composition, which is what we're about to do, the Yi, or it could be a mixture of both. And technically, since we are using this array for both functions and calculations, we can call it Z. So the only thing that will have to change is really when we're supplying our function with the array. That is the only time we will have to change our, yeah, I need to, yes, when you do change something, you need to remember to evaluate it. So yes, this should give me the same thing as before. So what I'm changing here is just to show you that the only thing you have to change, you don't really have to change your functions. We only have to change when we supply the function with the new variable we created, it needs to know where it's getting that variable from. Since if we put just xi, our liquid mole fraction, it doesn't know where to get that since we deleted xi. We renamed the liquid mole fraction to z. So again, sorry about the tangent, but I figured that was kind of important. So we're defining our dew pressure, similar to how we did it before. So defining our dew pressure, again, ideal, since this is Raoult's law. And remember, since this is dew point, we're starting with a known vapor composition. So Yi, um, again, this doesn't have to be Z, since it just takes in the first value it gets and calls it Yi within the function. But when we call the function right here, we will need to supply it with Z. Hopefully that makes sense. Um, so again, liquid mole fraction, and since this is the pressure, we will need to supply it with a temperature. Remembering once more with dew point, at a dew pressure, we have a constant temperature, and then we're increasing that pressure until we reach the appearance of the first dew, pretty much. So defining that, what else do we need? Oh yeah, we're just returning our function here. So what did we say our pressure was? It was 1 divided by, or I guess we could just do uh, Psat. So the sum of our saturation vapor pressures divided by uh, our liquid or vapor mole fractions, Yi, and make sure this is the sum of those, since we are using summation. So NP sum, I don't think I mentioned this before, but NP sum is how we do summations of I believe it's any parameter located within the parentheses, and then NP numpy is what is this line here. Kind of helps us do like here's array. I don't. I think sum and array were the only two we use. So it's just kind of basic algebraic functions we can use with our functions to help us here. So we're gonna do NP sum of the saturation vapor pressures, P dot P vap, that was supplied with our temperature times our, or I'm sorry, this is divided by our liquid mole fractions that we received as an input here from our parameters. So double checking here. Hopefully that should be correct. Okay, and then if we do calling our function, 2-point ideal, type in our D array, which again, we could have called it yi. It was initially xi, but we're keeping the compositions the same, even though it is now a vapor composition. And then what else do we need? The temperature, so 373.15, just like in the problem. Hopefully that's correct, 705,403. I actually have no way of checking this. This is the first time I'm doing this, so hopefully that's correct. I'm just curious what will happen if I type in what I did before. So I'm going to actually comment this out and try to do it the other way. I wrote it, and it technically should be the same. It's going to be, oh, I'm sorry, it'll be 1 over that. I believe that's what I wrote. Yes, 1 over the summations. So that was the liquid mole fraction by I times our saturation vapor pressures supplied with a temperature. Oh, okay. That is very different. So interesting. I believe there might be an error in how I derived it initially. So I will stop the recording here and pick it right back up if I find the error. Sorry about that. Pick up recording here. Yep. Okay. Okay, so I think I found the error. So let's actually just go back to our OneNote. Let me find where I put this. Okay. So I believe the order does matter in which you do separate these variables and isolate P. So let me make sure I'm still showing that. Okay. Um, yeah, so let's just kind of restart where we were here. Instead of just so we did say the xi, the liquid mole fraction, at the dew point equals 1. So we are correct in that substitution. 1 times the saturation vapor pressure equals our summation of our vapor mole fraction times our pressure, and we are isolating for this pressure. So let's go ahead and kind of move over our components here. So we have our, I'm just going to divide by the saturation vapor pressure. And now to isolate P, we are going to do, just kind of divide this whole section over, and that should be equal to our correct derivation. So we'll have our dew pressure is now equal to 1 over the summation of our vapor mole fraction divided by our saturation vapor pressure. So that should be our correct final answer. Getting some errors with the correct answer, doing it a different way before. So let's go ahead and code that. Commented out the wrong one. So again, with the pressure functions, all we're doing is returning our derived equation, which here will be 1 divided by the NP sum, the summation of our liquid mole fraction, yi, divided by our saturation vapor pressure, P dot B vap, for the supplied temperature that we put in the initial 2 parameters. So evaluating these, yes, we should get 89,000 pascals. And then now, to wrap this up, we're going to do something similar to what we did for the bubble temperature. So for the dew temperature, we're going to define our function like always, dew temperature, ideal once more, and same thing, since we are at dew point, we have a known vapor composition yi, so that's what we are supplying it with, our vapor mole fraction, and then since we're doing dew temperature, we need to supply it with a pressure that it will try to find that, or it will try to find the temperature for that given pressure. So let me make sure I'm recording. Okay. Similar thing, defining our, what did I call it before? P guess. Yeah. So iterating our dew pressures or I'm sorry, that's wrong. It should be P gas. It doesn't really matter what I call it here, but I call it the pressure gas. That's how I've practiced it. But in reality, you can call it whatever you want. And again, that is from a supplied temperature. And what we're going to be doing is returning um, our dew pressure from that supplied. What am I saying here? From our supplied temperature, because it needs a temperature to find the pressure, and subtract that from the pressure that we are supplying it with. Then that will try to find our T unknown. Same thing, we're going to be using root to zero out this function. So root takes the function as one of the parameters. So our function is p guess, then takes initial guess, call it 300 Kelvin. So we don't get just don't give it the answer right away. I don't know, kind of check the computer's doing its job. So that should be that. What am I doing here? Oh, I missed it again, semicolon. So it shouldn't do anything yet, right when I shift enter. I think what I did last time was return it. So when I call the function do T ideal, calculating the dew temperature, supply it with our array of Z, the feed composition. In this case, we know it's a vapor composition, but we're calling it Z anyway. And then if I supply it with our 89,000, it should give us the same 373.15 we got as bubble pressure. And that would be the, oh boy. One required T argument. What did I do now? Oh yes, this basic mistake. This function, remember that we defined it as having two variables. So not just temperature, but also in this case, the vapor mole fraction was the second parameter. If I call that, yes, converge. So we get our solution here. I'm going to go ahead and try to zoom in on that. Just the X attribute, the result, or the solution attribute, I suppose. Shift enter on both, and we should get 73.15. Awesome. So yeah, that is our code. Make sure we did everything correctly. So what we did, again, similar to the bubble point functions, for the dew point functions, we did the dew pressure first using our derived equation, which we've managed to fix and got the correct answer, as well as using that dew pressure function to do our iterating function with root, doing our guesses, I guess is the right way to call it. So finding the zero of this function for the value t, and then returning that value t here. And that matched our temperature that we supplied our dew pressure, and this dew pressure should match our temperature that we got and supplied that dew pressure with our dew temperature. So all kind of comes back to a full circle there. Awesome. So that has been part A of this problem. Hopefully there'll be some more fun stuff in the future.